Lab 6, Magnetic Molasses. Physics 2212, Griffin Davis. Introduction. The purpose of this lab was to observe how an induced current produces a new magnetic field which exerts a force on the source of the first field. We will also compare the results of the experiment to the values predicted by our code. Results. The experimental time that the bar magnet spent in the tube was 0.63 seconds, while the computational time the bar spent in the tube was 0.528 seconds. Fundamental principles. Our first fundamental principle is Ohm's law, in which voltage is equal to the change in flux over change in time. This basically shows how our change in flux is able to induce a voltage and therefore a current in a wire, or just an electrical field if there is no wire. But in this case, we will be considering the wire. And then the Ampere-Maxwell law, in which case the integral of the line integral of the electric field is equal to a constant times the enclosed current plus two constants times the change in flux of the electric field over change in time. So basically our experimental side was we dropped a bar magnet into a roll of foil, and then we measured the dimensions of the foil with the meter stick and able to do our code. And we used our phones and a recording in order to see exactly how long the bar magnet spent dropping through the foil. And our system was the bar magnet while the surrounding was the foil roll and everything else. Experimental results, we had an average fall time of 0.63 seconds. Not much else could be said. We just recorded it again using our phones. Computational results. So basically our code calculates a lot of different things in order to eventually get to that time. First it has to calculate the magnetic field produced by the bar magnet, and then calculate the magnetic flux by multiplying by area, and then it has to calculate the induced current, and then has to use that induced current to calculate the magnetic force from the tube on the magnet, and then uses all types of forces and velocities in order to calculate how long the bar magnet spins going down through the tube to get to the eventual time of 0.528 seconds. So errors, there's a little bit of error in this. A lot of it could be due to the human error of timing, or also like the error of our phones as well. Because basically the way we did it is we recorded it and then we slowed it down until we could see exactly when it left the tube. However, there is a difference in frame rate and the actual speed of things that could have impacted that. And then also we could have had an incorrect dipole of the magnet, whether that was bad calculations in previous labs or just having a different magnet. Like it's all the same type of magnet, but a lot of the magnets had chips in them and had like spots where the magnetic material was missing, which could definitely change the magnitude of the dipole. And then also magnetic interference, as was seen in our last lab, how there were some circuits in our table which could definitely impact the magnetic interference and the magnetic fields. What if the resistance was very close to zero? Well, if the resistance was very close to zero, that equation I equals V over R, as the V term is held constant and the R term is brought to basically zero, I would grow almost infinitely large, which would then in turn create an almost infinitely large magnetic field produced by the current, and which would then in turn create an almost infinitely large magnetic force on the bar magnet, which would make it barely drop or like drop at infinitely slow speed. What if holes were cut into the tube? If holes were cut into the tube, then there'd be less loops in order to have an induced current, which would mean less magnetic force on the bar magnet, and therefore the bar magnet would fall a lot slower through the tube. And conclusions: experimental time in the tube is 0.63 seconds, while the computational time in tube of the bar magnet is 0.528 seconds. This is due to our code. And as you can see, there's some difference. However, that difference isn't insanely drastic and can be described in the errors previously mentioned. Thank you.